All right. Well, I'm excited to be here. Actually, this venue is kind of interesting because this is where we traditionally do executive reviews. So I kind of have this like fear impulse. I feel like you're all going to tell me whether my plans are good or not. But really welcome here to Microsoft. This is a conference probably that I'm more excited about than just about anything. When I look at the lineup and I was kind of scanning over here, it's like this is an incredible conference. So many talented people in one place, and I think while this isn't maybe the flashiest work for the whole security industry, really the folks in this room and a lot of the presenters and what you're going to take out of here, you folks are the backbone of security, right? Big part of this room is really keeping the planet secure, so thank you for that. I also want to send a quick shout out to Rich, James, Matt in the back, who made this all possible. Putting together a conference like this is not simple, so I'm really glad that we have people like this, making sure it gets recorded, gets sent out, because this information is really critical. So it's a real privilege for me to be here today. So my name is Dave Weston. I'm the director of OS security here at Microsoft. Traditionally you would have called me like the Windows security person, but in reality we're doing a lot more. In fact, there's a couple of Microsoft talks here about us upstreaming various things in Windows, and we've changed a lot. If you followed some of the announcements today, right, we announced an Android phone. So Microsoft's really a multi-OS, really a secure platform company. And so while to be talking about our perspective on how to advance Windows security, a lot of this cuts across those various categories. So the first thing I want to talk about is, and this is really bright, how we are changing Windows to fit multi-form factors. So a couple of years ago, we actually went through a massive refactor under the hood, and for lack of a better term, to sort of Linuxify Windows, which is creating a real base core of a minimal set of packages or components that make up the base operating system. And the reason we wanted to do that is, most of the experience that folks in this room probably have with Windows is as a desktop operating system or a server, but it actually powers an enormous ecosystem of different device profiles. And the capabilities that we can extend are really now tailored based on that device profile. So for example, I might upstream into our base OS a number of OS capabilities, but they may not be able to be enabled or used in practice. I'm going to try to lower this one. There's a ring. Oh, I lost the, sorry. This is why I shouldn't mic myself. All right, that's better. There's a number of different capabilities that only come into play depending on the device profile. So for example, if you think about Windows for PC, in my viewpoint, that's by far the most difficult to secure. Everybody wants to run as admins. They want everything to be secure, but they want to run that Steam game from 1989 that was in 16-bit, and they get upset when they can't. So it's really challenging to kind of navigate that. Something like the Xbox, which I think Tony walked you through yesterday, that also runs Windows, but completely different security model. And this base OS component needs to be ready to be configured in any of those situations, and so we really focus on that. We're also doing a lot more headless workloads, so a lot of work on IoT and the edge. Again, the security profile and the features we might be able to enable by default there are quite different than something we would have for, say, the HoloLens or some more exotic devices. And so more and more, we've really decoupled the shell and the user experience, which enables us to reduce the attack surface in certain situations. For those of you who are Windows nerds, you might have noticed a few years ago, we refactored Win32K into multiple different versions. There's a base version with a smaller number of system calls, but if you need to do things like Windows APIs, you would use the full version, which has, I think, close to 2,000 system calls, so substantially different attack surface. So we've really undergone under the hood, I think, a real big engineering effort to refactor this into something that I would consider a modern operating system stack with the correct layering. And so that's really opened us up to make, in my opinion, much stronger security goals and claims depending on where the device is at and how it's going to be used. And so traditionally there's been almost this meme around Microsoft of our concept of security is really based on what's called a security boundary. How many of you have heard of this ephemeral viewpoint of Windows as a security boundary? And that is ultimately, hey, this is a construct in the operating system or a defining line in which we will back up by guaranteeing we will service fixes. So the traditional one is what we call the remote boundary, right? Which is being able to find a vulnerability that causes a DOS, information disclosure, or code execution across the remote machine boundary. That's a security boundary and we'll fix it. But then there are some other places where it's a lot more, for lack of a better term, ephemeral. For example, admin to kernel is big because Matthew Garrett did some really interesting things around upstreaming some Linux kernel changes recently. So there's a lot of people asking, will Microsoft change to guaranteeing they will fix admin to kernel issues? I'm not going to guarantee that today, but that is a place where we've selectively fixed or not fixed bugs in the past. And so what we're trying to do is remedy this by at least making it clear long-term where we intentionally want to go. And so I want to put in front of you sort of 6 security promises that we want to make, and some of these are aspirational, and some are closer than today than others. But it will hopefully make it clear where we are trying to go and where a lot of our security capabilities and investments map up to. So the first is we want all code to execute with integrity, and that's really a dual statement. The first part of that statement is we want to have mandatory code signing and code attribution for everything that runs user, kernel, or even dynamic languages. That's actually the simple part. The second part is this also applies to runtimes attacks, so things like ROP. In order to make the code, all code executes with integrity true, we also have to have runtime enforcement. So things like CFI, both in software and hardware, apply here. So there's a lot of investments that are happening to make this true. Again, probably some of you are sneering and saying, yeah, good luck guaranteeing that. But hey, we have to have a goal if we're going to get there, right? Number 2 is we'd like to make it the case where you can just no longer steal or spoof identity, period. And our first set of investments there are making Windows a first-class citizen of FIDO and WebAuthn. So we support multi-factor authentication in a number of different forms, both with hello and things like FIDO keys. But we also need to have storage of those credentials. So once you're authenticated, that's where the real fun begins. That's what Mimikatz and other credential tools target. We're doing a lot of work to use keys and other secure enclave technologies to try to store credentials once secure authentication has been made. The third area, and this is to me probably the most challenging where we haven't had as much investment in the past, that is making sure an attacker with casual physical access, we have a pretty loose definition around that, which is 10 minutes alone with something with exposed ports. Not someone with an electron microscope doing acid attacks or fault injection. It's a whole other threat model that Xbox does have. But good luck getting a PC made with good cost there. But we do want to get to the point where, as you're traversing an airport, you're leaving your stuff in the hotel room when you leave, that you can have a reasonable guarantee around security. So I'll talk to you a little bit about investments there. Another thing that we were working hard on, and this is something we learned really well from Xbox, is we'd like to get to the point where we can make a security guarantee around persistence of an attack. So we want to get to the point where, yes, even if you had, say, a remote kernel vulnerability and you were able to achieve code execution, if we reboot the device, that persistence is gone. Now, that's very challenging, but again, Tony talked to you a little bit about yesterday about how we're using things like XVD or permanent system partitions with hardware locks there. And I can tell you, we've done some red team activities testing some of these things, and they are much harder to break than even hypervisor boundaries. So another way of saying that is breaking the persistence barrier in a well-designed system is a cost driver for attackers. We don't think attackers have a lot of utility compromising systems that are regularly rebooted that have a non-persistence guarantee. The fifth area is we'd like to invest and make it much simpler to have isolation across all user mode processes on Windows devices. Today, I would argue that we lag behind some folks there on certain forms of the platform. Most of us are probably running admin on our devices. When you start up Notepad, if there's a code execution flaw in Notepad, you're going to be able to get the split token, get admin. That's not the situation we want to get into. On other operating systems, including Linux, you have mandatory access control, you have configurable system call filtering, you have a number of tools to configure a system there. That's the direction we'd like to go with Windows. And then the final piece is, all of this is great when you're thinking about a systems view on a single device basis. The real interest at this point is more and more assets are stored in the cloud. And so a lot of our customers are moving towards a concept of dividing their Windows networks around the concept of zero trust. And this is where attestation becomes really important, because it's all good and well if this stuff is turned on, but if it can't be integrated into the authentication process, then you're missing an opportunity to make a network level security claim. And so what we are trying to do is, for all the security properties that we're guaranteeing, making sure that we can have a hardware-backed claims or attestation claim around all of these properties. And we think in conjunction, if we can get to this place, and this is a multi-year roadmap, that would be Windows will have advanced substantially. So I'm going to talk to you about how we're starting on this mission. So the biggest problem with Windows devices today are not a whole bunch of flashy attacks. They're actually mind-numbingly boring attacks that repeatedly happen because business processes, compatibility, and things that happen in the real world. So most attacks occur because someone is running as admin and clicks a macro, right? That's not great, right? Especially Linux folks, the idea of just cruising around in root is unthinkable, but it's done every day on millions of Windows machines. So we have to attack that problem. Number two is a good chunk of malware attacks simply come from people executing unsigned code. So the most common attack out there in the Windows landscape, and we can see this from Defender and our various email services, are somebody generates a single binary per user. They ensure that that binary bypasses all the AVs by scanning it in a multi-AV scanner, and they send it to a user, they build some context around it, and the user clicks. And I bet every single one of you in this room are saying, that would never be me. Who are these silly, dumb users? I can promise you at Microsoft we do phishing exercises, and the most intelligent people I've ever met fall for this all the time, because part of that hubris that you have around being technically viable is going to lead you into taking the bait in the right situation. So getting to a point where you just can't being tricked into that on Windows PCs is a huge deal. If you look at mobile platforms, the idea that you have to be concerned about what you're clicking on is unthinkable. It's not even part of the paradigm. We need to get desktops there. The third bit is, if it's not unsigned code, the next largest problem, and they actually oscillate, is passwords. Just the fact that you have a symmetric secret that you can be forced to give up or tricked to give up is a huge problem. And so that's something we want to attack. And the last thing is, because of compatibility and other reasons, we don't have a central source of an app store where you're doing validation and attestation and things like that. I mean, apps can be in various forms. I've seen apps with CFI turned on and no ASLR. ASLR and no depth, CFI and no ASLR and depth. So making consistent claims there is really, really difficult. And so even when we have good services in the system to make things secure and attack memory corruption, in most cases, if you look across the breadth of an app catalog at like an enterprise, they're not being used. That's a huge problem. So the way we dealt with this is by introducing a mode, first targeted at consumers, kind of the people buying the 500 and below devices, is Windows 10s. And Windows 10s, it wasn't a flashy security model. Most of it was take what we already have in Windows and turn it on. And a lot of the reasons we were able to turn it on is we restricted it to the App Store, so we knew, hey, this thing is going to not load kernel drivers. It's going to have write its state into predictable locations so we can roam that data or make claims on it. And we did 4 things. Turned on mandatory code signing from the store only, did some basic scanning and analysis on the onboarding. We support a completely passwordless mode, so if you're using like a Microsoft account and you've got a FIDO key, you can provision the whole thing without ever entering a password. So that's pretty cool, and any website that supports WebAuthn will just magically work. I actually do this a lot, and it works really well. The third thing is we blocked not only unsigned code, but we also limited scripting and other attacks, which are a common way around code signing. Hey, it's cool if you have code signing, but if you sign the interpreter, that's probably not going to work so well. And the fourth thing is we've actually created a mode where you can be adminless. What does that mean? Well, most of us that use Windows PCs are cruising around in admin because we need to do things like change the color of the desktop. So we've actually created a mode where you can do most of the admin-like things, but you can't do crazy things like read and write memory or debug processes if you're not a developer, and more on that. And so we introduced this on millions of machines, and guess what we found? Have Defender on those machines. We haven't seen a single widespread detection of malware. Now, I'm not up here making crazy claims like you can't find a way to get malware on that. I'm just saying in the normal user flow where you're clicking things and getting phished and things like that, we are not seeing malware like we would on a normal desktop. So this is a really good example of what Windows actually has a lot of security features. Really the challenge is in finding how to get those security features turned on without breaking what's cool about Windows, which is you can run 30 years of software in the way you want it. And so a lot of my job and a lot of what you'll see here is me dancing that thin line of trying to improve security while not breaking why you would use Windows in the first place. And that's really the challenge. Now, 10s didn't really catch fire in, I would say, power users groups. And that was mostly because people were saying, I don't want to use the Windows Store, or the app I want is not there. And just recently, we've introduced some really interesting ways to leverage 10s that I think will open it up a bit. What you're seeing here is first, me running a feature called Windows Sandbox, which is a lightweight hypervisor-based container, which is full classic Windows, but it is interstitially woven into the desktop experience, kind of like a KVM or a Hyper-V or something on the desktop, where you kind of can view that and get it started really quickly. And you can do anything you want in terms of running Win32 in there. As soon as you close it, it goes away, it's non-persistent, it's gone. We also have a service where you can run Windows apps in the clouds for a reasonable price. And of course, you can just sign your apps and sideload them if you want. So this is a good example of, I think, us starting from a place of we're going to get better on the practicality and increasing it. Now, I want to talk to you about our journey and some of the challenging problems we have on increasing code integrity and where we're at. So traditionally, people dig code integrity. They dig the concept. They're like, hey, I want to restrict down to an allow list of applications, but they don't know how to do it. So most of the enterprise customers that you target out there, they don't really have a good handle on all the applications that are run across the ecosystem. For example, Microsoft, we have close to 1 million machines here that are running various forms of Windows, and I would not say that we know every single application that needs to run at all times. So with 10S, we thought, let's start with a good secure base, and then we'll allow users to add either from the store or from their sideloading applications that they can take advantage of. The security challenge with that is just turning on code integrity for all Microsoft inbox binaries doesn't do that much for security. The reason is we have PowerShell, we have VBScript, we have macros. All of those are Microsoft signed binaries. So if you just sign those and call it a day, you really haven't done much for security. So the first thing we had to do when securing 10S, and this is also what we publish on GitHub for our customers, is kill all those proxy binaries. And we have a group of finders. They are just masters at finding some weird binary somewhere that has one interpreter funky function, and they can use that to execute code. And this is like what they do, and we love them. The second piece is there's a whole set of proxy binaries that you just cannot kill. And the reason is they might actually perform a function in the OS that is critical. A good example of this is LNK files. So when you create like a shortcut, a link on your desktop, you're actually triggering a COM object that handles LNKs. And if I kill that, all your shortcuts don't work. But if I leave it there and you double-click an LNK file, you're going to end up with arbitrary code execution. And there's actually lots of malware attacks that focus on this. So in order to sort of clarify this, what we decided to focus on was rather than making claims around all code integrity and restricting all code, we decided to focus our security guarantees on what we call first-order code execution. That's another way of saying we want to focus on blocking attacks that started from the internet, getting to grandma or grandpa, and then double-clicking it. Because the reality is the vast majority of security problems for the vast majority of users is going to be addressed in that way. And the way that we figured out, how to do this is, for these dual-use properties that we can't just block with a code integrity policy, we decided to use the ability to infer the source of that extension and determine whether it should execute based on the source. So for example, if we were to take a malicious user sending you an LNK file remotely, the first thing we would do before we execute that LNK file or do any instructions is decide, is it a dangerous extension? If it's not a dangerous extension, we'll just kick it off. If it is, we may block it, but we will only block it if it comes from the internet origin. And the reason that that's important is you can create LNK files local on your desktop, everything is cool, works as normal. But if you get an LNK file that's marked as coming from an internet origin or a network source, we will block it, and you'll have to go through an experience to remove that. So we kind of, again, this is us kind of navigating that crazy tightrope of increasing security without breaking an operating system that wasn't necessarily designed, optimized for these types of cases. And this has actually worked really, really well. Okay, so the second part of restricting or ensuring integrity of code is dealing with memory corruption vulnerabilities and dealing with exploitation. And there are really 4 things that we're trying to achieve here that we think are intrinsic to solving this problem. The first is we think control flow integrity is really important. As long as you don't address that and you have memory corruption vulnerabilities, you're not going to have an effective approach. The second, which I touched on, is ensuring that we have signed code only. The third component, and this is increasingly important, is we look across the exploitation and threat landscape, is enforcing read-only data and data immutability for critical data structures. And the fourth thing, which is the most challenging but arguably the most effective, is eliminating bug classes. I've been making arguments to my management we should just rewrite Windows and Rust, but they haven't gone for that so far. So in lieu of that, I got to do all this other stuff. So when it comes to control flow integrity, there are 3 big problems we still have to solve. The first is dealing with dangerous call targets. And I'll elaborate on what I mean by that. So back in Windows 8.1, we introduced, I think, the first OS with kind of a mainline support for control flow integrity. And that was called a feature called Control Flow Guard. We love to add guard to any kind of feature name. It's like that's our brand. And what Control Flow Guard did was a coarse-grained approximation of CFI. Again, this is us straddling, we got to increase security, we can't break every app on the planet. And what CFG did was pretty simple. At compile time, for every indirect call target, so when you take an address and call through it or jump through it, we would add that to essentially an allow list, something we call a bitmap that gets shoved into the PE file. And then at runtime, every time there's an indirect control flow, we make a call out to say, hey, is this indirect target in that list? If it is, we allow it. If it isn't, we crash the process. Pretty straightforward. The challenge with CFG is in order to allow for intramodule calls and basic general compatibility, we over-approximate, we overfit. We say, it's not just indirect call targets that we know at the time of compile, but it's also anything exported by any function. And so you can imagine attackers at first were kind of stumped by this. So we saw exploits break from this. But after a while, they figured out, well, I can find proxy functions that do interesting things. I'll just call through them because they're valid somewhere in this process's address space, so it'll work. Or if you look at kernel 32, imagine if you corrupt a function pointer and then you can just return to anything in the exported kernel 32 API. Well, it turns out that's most of the Windows native API. So as long as you think about it hard enough and it's annoying and you write a couple of Python scripts, you can probably figure it out. So while we thought this was good and useful for a long time, turns out it's not going to solve all of our problems. So we thought long and hard about how to fix this. Again, finding a compromise between performance, reliability, and security. And so what we came up with is, again, we love our guards, is extreme flow guard. This is a red team joke. I don't know how it's made it into like the official name, but for now it's called extreme flow guard. And XFG is essentially fine-grained CFI. So we're trying to solve the problem of there's way too many valid control flow targets, and essentially all we want to do in a nutshell is reduce that search space to as small as possible. It makes sense, right? And the way we ended up theorizing how to do this is we said, okay, well, at the time of a control flow transfer, what's the most unique attribute that we can hone in on and create a policy around? And we determined the thing that we thought was the most reasonable here was to create a type hash based on the function definition of the call target, as we see it at compile time, and create a hash around it. And by creating a 55-bit hash around this, we can basically add just a couple cycles to each check, but we can reduce the search space, depending on the binary, by as much as 100x. And so essentially what we do is we take for a standard C function, we take the return value and the type of the arguments and that are defined in the function prototype, and we generally hash them. And then we just stick in before the indirect control validation, we put in code, which is immutable and can't be modified by the attacker. We put in code the hash, and we pass it off to the dispatch function that compares the function prototype of the new target function from what was embedded in code. And what that means is, if you have an arbitrary corruption, for example, like a heap target or a stack overflow, and you overwrite a function pointer, now you have to overwrite it with a RVA or a virtual address of something that matches this function prototype. So you go from like anything in the export table to 1 or 2 functions, hopefully. So this makes an attacker's life a lot more miserable. They may be able to, in the fullness of everything in the process address space, find some functions to string together. But again, our goal here is to make it as expensive as possible. And we have a lot of attackers whose kind of personal experience went into building this. And so we think this is actually super useful and something that's relatively cheap to build on the existing infrastructure that we have. So in the end, this 55-bit hash is probably not as full as we'd like it, but again, it balances the performance of what we'd like. And we approximate, again, on average, in aggregate in the binaries we've looked at, about 100x. And so this isn't in build today. This is something that we're just getting into the compiler and targeting, but we expect in some upcoming Windows versions to ship this. Now, it's cool that we dealt with what we call forward control flow, right? And in most compute systems, you have forward control flow and you have rearward. The easy way to think about that is calls and jumps. would be mitigated by forward control flow. RETs would be mitigated by rearward. And so the second area that after we shipped CFG that we saw attackers kind of gravitate to was rearward, which wasn't validated at all. So a very simple and clever attack you might see at something like Own the year we shipped CFG was they would just stop using calls or jumps at all. They would get an arbitrary read-write primitive that would allow them to corrupt the stack. They would replace an entire stack frame with rets to things that they wanted to call. So it'd be like ret create file, ret execute file, ret write file, et cetera, et cetera, et cetera. And our first initial attempt at mitigating this attack surface was a really cool experience for me, and I'll just hit it in a nutshell. Is we had co-designed this feature with our Silicon partners where we wanted what's called a hardware shadow stack. So in a nutshell, it's actually relatively simple. Every time we push a ret on a new to create a new stack frame, we obviously have our standard software stack, but we have a hardware restricted data structure that keeps track of those rets. And every time the software stack returns, it asks the hardware stack, hey, cool, is this the same return address that I pushed on originally? And so that prevents you from just getting a write primitive or replacing a whole stack frame, because it's got to map up with something that was in normal control flow. And so that works really well. The challenge is it takes future silicon. And future silicon is amazing, but man, does it take a long time to get to market, right? There's a lot that goes into fabricating silicon. I probably don't have to tell this room. So we thought, hey, we're smart people. Maybe we could just do this in software. So we came up again with another guard called return flow guard. Very, very creative name. And we thought, you know what we can do here is we can create a shadow stack. The challenge of the shadow stack is if it's in process memory, attackers can find it, right? They can search, they can infer, they can side channel, all that stuff. And we thought, you know what we'll do is we'll take the memory manager and we'll hide it. So when you call virtual protect or any of the other virtual memory functions, we just won't return where the stack is. And in a 64-bit process, there's a lot of places to hide the stack. We can put guard pages in front of it and after it. So if you try to scan for it, we thought we figured out everything. So we actually went to our management. We're like, we got to build this thing. It's going to be awesome. All the red team people on board. In fact, they designed it. So the best people at attacking also designed this. And we got support for this. We put in all the builds. It was in Windows Insider. We were like, this is awesome. You know, everyone on Twitter is like, this is great. And then we found a race condition that was a design flaw, period, flat out, where we knew how to bypass this thing. And this was honestly my proudest moment at Microsoft. We went to our management. We're like, we're going to pull it out. And probably nobody would have stopped us, right? Nobody was enough into memory corruption that would do this. And in fact, there were lots of like government agencies, the other people were like, keep it in, man. Like, it's not perfect, but it's pretty good. We took it out. And for me, the reason that was important is it was a time we reached maturity to actually evaluate our own stuff without any external feedback. And we reached a point where we're not going to ship stuff that we can't stand behind to those promises. So that was a really cool situation. It's gone now. Good news is, you know, we think we'll have control enforcement integrity, which enforces this hardware shadow stack in the near future. And the combination of what we did with XFG and CET, we think will help us substantially. But it won't solve the problem, and I'll tell you why. So attackers haven't just been chilling. They didn't go get jobs at McDonald's. They figured out other paths here. And the new hotness in memory corruption is basically to do pure data corruption. And we know even from our own internal experiments, if you have an arbitrary read-write primitive, right, so you use a memory corruption to corrupt an array length, and you just think, what can I do with the fact that I can index arbitrary memory and write to it? You can do a lot. So you can do things like call all valid functions, but change their arguments. Right? Just open up your mind for a second. What can you do with just pure data corruption? So control flow integrity is restricted to what's actually called in the program. But if you control the arguments and you can tamper any or modify any data structure in that process's memory, you can do a lot. So we've created, just in JavaScript with arbitrary read-write, full kernel exploits. So we've like created an RCE in the browser, and then we've called enough functions going to the kernel with modified arguments to actually construct a second exploit without ever dealing with control flow integrity. So this is a very high bar, right? I'm not saying at all that we've solved things. So we got to solve data corruption, but it's a long journey, and I'll tell you where we're starting. So the first thing we want to solve with data corruption, or at least mitigate, is kernel-based data corruption. And kernel-based data corruption is even more acute than the browser scenario I talked about today because there's a lot of targets, right? But when you don't want something to get messed with, you shove it into kernel. So if someone gets in a kernel, it's kind of a bad day, right? You haven't thought about segmenting privilege in a kernel, it's a kernel. But the challenge with the Windows kernel is, again, for compatibility reasons, we have all number of tens of years of peripherals with crazy signed drivers. People don't know how to validate ioctls before they accept them. So we have a lot of attack surface there. So what we see with attackers is when we push something in a kernel, a security attribute, for example, our protected process, which is this bit in the E process, which is our fundamental process structure that says whether you can debug something or not. What attackers do is they say, that's cool. I'll bring this VBox driver from 2007 that's still valid. I'll load it up. It loads because it's validly signed, right? But it has an ioctl, arbitrary write, and I'll just use that to overwrite that bit. Now I'm off to debugging. And it's really hard to have a secure user mode system if everyone's admin, and the additional layer we added on admin to stop people from debugging can also be corrupted through kernel. So we do obviously have solutions for this. You can use things like code integrity to restrict the drivers that can be loaded. Most consumers are not going to do this. So the path that we're kind of working on now is looking at how to make some of the most critical data structures in kernel immutable. And it turns out when we have virtual secure mode, or our kind of secure enclave, secure world infrastructure, RT turned on, we actually already have hypervisor control of the page tables. So we can actually just decide, hey, these physical pages, they're immutable after initialization, and we're going to lock page table modifications so you can't just use your arbitrary kernel to mess with the PTEs. And what that looks like in practice is you can actually use this API, MM Protect driver, and call it on either static data, or in the future, create a dynamic pool-based allocation that's backed by a static physical page. And the secure kernel infrastructure, which is essentially RT, will handle handing out the allocation and then locking the page table state so it's immutable for the lifetime of the OS. And what that means is an attacker who's running an admin who then loads one of these 3 drivers that are frequently abused, when they go to corrupt static data or dynamic data, they'll take a page fault and it won't work. Now this is really cool, but it's obviously not sufficient because the handful of things that we can go and protect today probably needs to expand out to a huge set. So I watch closely what's happening in, say, the Android or iPhone or iOS ecosystem where they've got some of the similar things, and constantly attackers are obviously looking for new places to go. But until we have a fundamental solution for this, something like Cherry, which I'm going to talk about today, this is like one of the paths we're going to go on. So we think this is actually a good start to making data corruption at least not as useful. So I better jam. I'm going to move on here on this, how we're increasing isolation. So the first thing I wanted to talk about is this concept of admin lists. So I'll just start by saying this is kind of almost a non-starter on desktop operating systems where people want the fullness of legacy applications. There's tons of legacy applications that never got that UAC was a thing, so they never updated their applications to use alternatives to admin. But on newer operating systems, for example, 10S or the 10X we talked about this morning, there's a possibility of using admin list mode. And in a sense, it's really simple. So we take the existing admins today and we convert them to something we call device admin group. And device admin group has basic privileges to do things like change the desktop background, maybe open some logs, open control panel, the things you would expect. What it doesn't have, which is arguably the most acute challenge with admin today, is it doesn't have debug privilege or read-write privilege against other processes. And the reason that's critical is like the script for compromising a Windows network for the last 20 years is like, get someone to click a macro, you're running an admin, read process memory on the thing that has the user's passwords or the hashes, grab those, rinse and repeat, right, by just expanding out your network footprint, and pretty soon you are changing elections or something like that, right? So it's a really big deal, right? It's a really big pattern that we want to break. But by saying, by default, there is no way to do that, and by the way, it doesn't cause any more user friction because you can still do most of the stuff you need, it's actually a pretty great solution to this. Obviously, we're going to have developers who want to debug or do things where you have power users. Hey, we have desktop, or we can introduce unlocked modes. So this is really important. Again, it's not the flashiest feature, but from a bread and butter standpoint, making this the broad state is absolutely one of our top goals, and will solve a lot of our security problems. Now, the thing that admin list doesn't solve is when you have memory corruption issues, where attackers are getting arbitrary code execution, and now they want to move out of, say, a software sandbox. They can move to target the kernel. Linux, for a while now, has had things like setcomp BPF, where, hey, if you really worry about a process, say your browser or an Office application, I don't know if LibreOffice or something like that would have isolation there, but not only would you want to isolate and restrict privileges, but you would also want to isolate the kernel attack surface. And the reason is about 5 years ago, when the user mode sandboxes became ubiquitous, attackers just got used to, like, hey, if I want to write an exploit across a network boundary, I'll have a remote code execution exploit, and I'll have a kernel exploit, and that'll get me out of any sandbox. Now, Windows has an undocumented long list of system calls, so creating something like setcomp BPF is not as straightforward as it would be on a POSIX system. Part of that is we just don't even have documentation for our native system calls, so describing to a developer how they might write a policy is difficult. So in a true Windows fashion, we said, we have a hypervisor. We can actually tailor that hypervisor to create essentially a copy on write version of the operating system. And that version of the operating system can have a reduced attack surface because, yes, we'll mimic a kernel to this application that's being isolated, but you won't be able to target the system call surface of the host. And so our first introduction for that is what I'm showing you now, which is Windows Defender Application Guard. It's essentially a lightweight hypervisor-backed kernel, which has a remote desktop channel that's channeled over the hypervisor IPC, which looks and feels like it's a native application, rewrites quickly, supports direct 3D acceleration and other constructs that make it a full citizen of the operating system, but it has its own kernel, and thus the system call attack surface is reduced. So again, in true Windows fashion, we don't just have one container format, we have 4. The one I'm talking about here is Krypton. So again, Krypton is a copy on write, lightweight VM. It's actually also used in some of our Docker and Kubernetes implementations. And really what sets it apart from a standard VM is 3 things. The first is what we call direct map. So when you go to start up our Krypton VM, it doesn't just have its own copy of kernel 32. That would be pretty fat. Instead, what it does is when it goes to load kernel 32, it asks the host, hey, do you already have a copy of that in memory? And if so, can you just map the page in? So that's what we do. And direct map gets us to having very small copies of VMs, right? You're used to like VHDs or things like that if you use Hyper-V at all that are multi-gigabyte. I think at last count our VHD for Windows Defender Application Guard is like 13 megs of registry entries. That's because we just don't have to carry the images we ask for the host. And that's fully secure because it's not bidirectional. The host just maps it in one direction. The second thing that we addressed is having to have physical pages pinned. So in a traditional VM world, you would say, like, I need 8 gigs for this thing. And then we would hand over 8 gigs of physically pinned pages. And all of a sudden, you have to have this monster laptop with like a 130-watt power supply, and you're on the plane trying to plug it in, and that green light's going. I'm sure you've been there. Physically backed pages are not great. So we actually went into the memory manager and decided we can do page-backed memory for VMs and just dole out what people needed. So we have a wizard who does our memory manager, and he was able to work out a way where this essentially is just like another process. Even though it has the properties of a VM, from a memory manager standpoint, it looks very much like a process. And the third thing we targeted to make this widespread is an integrated scheduler. So again, traditional problem with VMs is they suck a ton of battery life because they're sitting there doing things idle in the machine, and there's a separate scheduler for the main host scheduler who's like, I can't freeze this thread or freeze this process or hibernate this thing because I don't know what's going on there. So the scheduler actually now natively supports this concept of scheduling workloads inside of these lightweight Krypton VMs. So when you get down to it, we actually got to the point where we can have multiple versions of these VMs on like an 8 gig laptop, and the performance is acceptable. And we're able to today put the browser in there, and we'll have other processes that, and applications that we'll put in there long term. And we also have a feature called Windows Sandbox, which is based on a Krypton VM, which is like pretty instantaneously starting separate world that you can do whatever you want. So the next thing I want to talk about is how we are trying to make stronger persistence guarantees. So firmware security issues are a major challenge. And I would say for us, they reach an acute point when we introduced RT based on a hypervisor. And our hypervisor isn't a traditional client-based hypervisor where you might be able to block out access to ports or MSRs or SMIs. we're running, in a sense, side by side by the operating system. So things like SMI handlers are completely on the attack surface. So if a firmware has a vulnerability in an SMI handler, you can use that to get code execution as SMM. Now you can tamper the hypervisor, kernel. It's a bad day. And so we started to see a lot of attackers migrate there. And it's not just for the privilege. It's also because, obviously, enterprises are spending a lot on some of these kind of magical detection solutions. And most of those cannot view, they don't have visibility into firmware. And so for attackers, this is a double whammy. It's like, cool, so I get code execution in this highly privileged thing that has lots of lines of code on the attack surface that probably isn't audited very well. It doesn't have the ability to be updated. Oh, and by the way, there's like no logging or detection there. Sounds pretty good, right? So when I talk to people who have kind of spooky backgrounds, they always know a ton about firmware. Always. You're like, so why can you quote me the EDK2 like function list? And they're like, I can't talk about that. But that was enough for me to say, we need to spend a lot of money securing the firmware. And so there's been some pretty good examples of that. Alex and other folks, tons of people in this room have contributed to that. So that's great. So we've learned a lot. Now the question is, what do we do about it? So we kind of went back to an old thing to start. We thought there are lots of different ways to mitigate this, but there are a couple of problems. Ultimately, we want to kick firmware out of the TCB. We don't want millions of lines of code that is challenging to update, that's different across all these OEMs, that's potentially written by people who don't have a ton of experience. Now, most of you in this room are probably like, why didn't you use core boot? What about U-boot? There's lots of things and value propositions that the Windows ecosystem is latched onto around that. And so, hey, I'm a fan of core boot and U-boot and every other reduced attack surface, but the reality is that's not going to happen overnight, right? Hopefully we'll get there. So the theme for me is I've got to walk that tightrope between security and the existing realistic ecosystem. And so we looked at Intel and some of our other silicon partners, AMD and QC, and we thought, hey, DRTM might work here, right? So we can allow the firmware to still be there, but we can reattest the core components we have, which is the hypervisor, the bootloader, and the kernel, assuming breach, assuming someone got into the firmware, reattesting that and using CPU-based trust to make a security decision. And not only would that help us with our problem here, but we could also send those signals up, whether via the TPM or some other hardware root of trust, maybe a T, maybe VSM. We could send the PCRs, the logs, all of our measurement data to the cloud. And now not only can the operating system make use of that and decide whether to load or release a key, but we can actually have network-based authentication based on CPU trust. And that is very popular with most of our customers who are looking to moving away from these perimeter-based firewall IDS networks to direct cloud authentication. Now, whenever I say DRTM, those of you in this room probably jump to, well, I remember Joanna Rotowska wrote this paper in 2007, TXT relies on SMM, it's a fail. I'm not the smartest person in the room, but I'm not so dumb either. So we thought a little bit about how SMM can work, and we worked with our silicon partners to address that. I'm going to talk about that in just a second. So the first thing I just wanted to point out is, even in our own testing, we've done a lot of red teaming work around SMM. And even really good firmware code bases, for example, we looked at Surface maybe 4 or 5 years ago now, we fixed all those bugs, but initially we were able to find some bugs in there and exploit even our first party products. So we agree that SMM is definitely a problem and firmware is definitely an attack surface. But we wanted to find more of a holistic solution for this. So again, we partner with a number of silicon partners, and this architecture will look vastly different on, say, something like ARM than it will on AMD and Intel, but it's basically the same concept. Eufy's a dumpster fire. we let Eufy start our boot manager and our WinLoad, and at some point we're going to make senter or the equivalent in something like Skinit, and we're going to trigger an ACM or the equivalent in an equivalent T. That ACM is going to leverage the hardware and load our measured launch environment. Our measured launch environment is then going to use various components that they can measure in. For example, what are the boot command arguments? Is SMM initialized and does it have its page table locked down, which I'll look at in a second, or any other property on the system that we think is required to make any kind of statements about boot trust. That will then carry along to hypervisor and load the secure kernel, and now we've essentially bootstrapped trust into RT, and things are good. Now, the traditional challenge to that is all of that is undermined if you can attack SMM. So if you can find a vulnerability in SMI, which, to be honest, is not that difficult in today's landscape, all of that goes away. So we partnered with a number of Silicon partners. Intel has the name Intel Runtime BIOS Boot Resilience. And essentially, what we've come up with here is we wanted to have the privileges or the privilege restriction of an STM. But frankly, an STM is really challenging. You have to be like the NSA and upstream it to core boot or something to make it work. We couldn't find anyone else who really made this work with performance in practice. So again, we thought, what's the most critical thing here? And the most critical thing we decided is if there is an issue in SMI, we want to make sure it can't tamper hypervisor memory and can't touch OS memory. So in a nutshell, the standard here, and again, it varies across the silicon vendors, is we want to make sure when we're making statements around our firmware protection being turned on, that not only is a dynamic root of trust management in place that's pretty close, a generic version of what I just showed you, but also SMM paging is enforced and restricted, and we can attest to it. So the paging says when you switch into an SMI context, all of your writes need to go through a page table construct, and that page table construct is initialized at runtime, locked by hardware, and eventually attestable. Very important is that it's attestable at the time that the DRTM is triggered in SINIT or SEnter or all variants of that. And what that allows us to do is say, even in the event, maybe the likely event, that there's an SMI handler vulnerability, it's restricted to NVRAM only, and in most cases when we've looked at that, restricting to NVRAM only makes it very difficult to use that to compromise the hypervisor or the operating system. And so by enforcing this SMM protection as part and parcel of our dynamic root of trust security claims, we think we've upstream as an example, and so I put some links in there for folks who want to follow up on that. We actually have 2 products already in market and many more to come. The Toughbook 55 has DRTM enabled initial versions of SMM isolation, and the same thing with the HP Dragonfly. So these are really cool PCs that have, out of the box, the secure enclave and dynamic root of trust, which is a good example of us making progress, I think, in the ecosystem. So to blaze through here with just a few minutes left, talk to you a little bit about what we're doing around physical accesses and the challenges we have here. So it's not easy being Windows. The stuff we just got everywhere is now in some cases being undermined. Good examples of that are Ulf Frisk and a number of other people have done some really amazing work illustrating how you could commoditize attacks against DMA. So they've mostly focused on Thunderbolt, but all of this would apply to FireWire or any other DMA port or protocol you want to apply. So essentially they've been able to use FPGAs and other relatively cheap and available devices to masquerade as valid Thunderbolt devices. Once you plug those in, you have read-write primitives, and then you can build really cool abstractions on top of that to do things like bypass the lock screen, inject code into memory, et cetera, et cetera. And again, back to our limiting casual physical access to being a non-security event, this undermines it, because if you look around the room, most of us have an exposed DMA port. Not that sweet. There are also multiple attacks physically against BitLocker. An example of this is frozen RAM attacks. I wouldn't necessarily put this in casual physical access, but it's certainly right on the cusp. But and also attacks against discrete TPMs. So sniffing against the LPC or SPI bus is now very possible with a $20 logic analyzer and access to GitHub code. So this is something we need to address. So where are we going with that? The first thing we want to solve practically is we want to address some of the common DMA attacks. And so we're doing that in what is relatively straightforward and logical way. The idea we have today is we'll start up the IOMMU in firmware that supports it very early in boot. And there is always a race condition between the IOMMU starting and some access for DMA. So we use things like the bus master enable bit to block access of any new DMA devices until it can do a secure handoff to the IOMMU, and then we'll boot the system. And the idea there is the IOMMU will now stay in a lock state that won't accept any new DMA devices. We call that DMA remapping. It's the standard, at least for certain protocols like Thunderbolt, et cetera, until the user unlocks their machine. When they unlock their machine, we'll be able to discover new Thunderbolt devices. Everything is cool. When they lock their machine, you can't introduce a new Thunderbolt device. It's a pretty logical and simple manner for doing this. It does require you to run a system that has IOMMU and run a pretty recent version of Windows. But we think this is a pretty reasonable approach to the initial most acute problem, which is Thunderbolt. Over time, we want to take this DMA remapping capability and drive the ecosystem across M2 devices and any other DMA-enabled device to support something similar. So this is where we're starting today, and there's a really simple way, if your machine supports it in the UI, to just go ahead and turn on memory, what we call memory access detection, which helps with DMA attacks. Second thing we want to do is much more difficult, which is if you look at the generalized TPM problem space, and you look at some of the frozen RAM attacks that are much more difficult to solve in software, obviously, we've got another approach. And that is to do a second layer of encryption on your most critical files. So today, almost all of our encryption is done at the volume level. So BitLocker basically looks at the volume or the partition, if you like. Depending on how you configure it, you can either do pre-boot authentication, or you can just use measurements in from your TPM to release the key, and it does this at a volume level. The issue with that is if your device is up and running and the volume's already decrypted, if someone sticks a DMA device in, or if they close down your machine and do a frozen RAM attack, or they sniff it across the LPC bus, they can actually play back the same measurements or hashes and potentially get the key unlocked. That's not great for physical attack protection. So what we decided to do is work to create an API that would enlighten sensitive applications, so things that have your health data, your sensitive text messages, your email spool, whatever it is. And essentially, this second layer of encryption ejects the key whenever your machine is locked. And that key is based on a physical property, something in the TPM, plus a piece of knowledge that you would know, like your PIN. And so those files can only be decrypted when the user actually types in their PIN on their machine, and the files are decrypted. So essentially, when you lock your machine, your most sensitive files are re-encrypted, the keys ejected from memory, so frozen key attacks, sniffing, other things are no longer possible for the specific data elements that are encrypted here. The challenge with this is obviously Microsoft is starting by enlightening our own inbox applications for upcoming versions of Windows to do this, but we've got to get the whole ecosystem on board, which will take some time. But we think this is a powerful and pretty elegant way, from a user perspective at least, for solving that problem and dealing with data protection at rest. In 4 minutes, I'm going to run through how we do user identity protection and what some of the challenges are today. So I mentioned this, but one of the most acute problems, if not the most acute problems in security, is phishing. And we actually see this oscillate. Attackers don't really care how cool or flashy their attack is. They care that it works. Phishing still works. I see the statistics even from Microsoft. It still works at a mass scale, so people still do it. So in our estimation, the best way to have no phishing is to have no passwords. And so we've been working diligently to enable Windows Hello as a FIDO2 authenticator, which would allow you to create essentially no user exportable symmetric secrets, so no passwords, and be able to use any kind of FIDO2 authenticator, whether it's an Android phone, Windows Hello, a FIDO2 key, to not only provision your identity on the machine, but to log in to the machine itself, as well as any WebAuthn compatible websites through something like Edge, Chrome, or Firefox, which all support the WebAuthn standard. We're also working closely in Azure Active Directory, also Google, Facebook, all the large-scale enterprise identity providers and consumer identity providers are on board here. So eventually, we think we'll get to the point where you can log into almost any website with a single identity that's hardware-backed. Now, the challenge with Windows Hello is anything that passes through software could potentially be snagged by a piece of malware or an adversary on the machine. And so our original approach for Windows Hello, and this includes Windows Hello as a FIDO authenticator, is to do feature extraction, template construction, matching, all the things that go into having a biometric stack in pure software. The issue with that is there are multiple threat issues here, especially with an attacker who's running at full admin. So they could intercept and replay those. They could tamper with the biometric matching and make matches pass when it shouldn't. There's any number of things that can happen. So the obvious approach here was to take most of this out of software and put it in a T. But again, making it so we can do this without having specialized hardware that we have to push across the ecosystem is a real challenge. So our smart team, lots of folks in this room actually, what we came up with was using the virtualization stack and the hypervisor to segment both our input stack and all of our biometric stack, the input stack to the biometric stack into a secure world using virtualization-based security, which would work across any Silicon platform that supports virtualization extensions, which at this point is all of them. And in a nutshell, what we can do now is fingerprint, Face ID readers, cameras, the things that would input biometric data, talk directly to the secure world, and the input stack doesn't traverse the normal unsecure world where an attacker might be able to get access to it. And all of the feature extraction and matching happens in that world, so it mitigates most of the tampering attacks. So if we look back at that original threat model, secure input deals with a lot of the replay and injection attack stuff. VBS isolation deals with a lot of the tampering. Encryption in VBS deals with the modification of templates, and VBS isolation as well as padding deals with the remainder of the attacks. So in essence, we think when we can get this mainstream, we've really secured identity at a much broader scale. Again, FIDO Alliance is going really well. It turns out lots of people are concerned about phishing, and so I've never seen an industry, especially competitors, come together so quickly with such a complicated standard. So this is really great. This is, I think, supported really well on Windows, but I know it'll come to Linux, it'll come to Chrome OS, it'll come to Android quickly. So there's actually some broad support there. Now, I've kind of run you through the 5 security promises we have and at least what we're doing towards getting to that. And the final piece, as I said here, in our strategy is to make sure all of this is attestable so it can be worked into zero trust concepts. So making tamper-evident detections or making Windows tamper-evident is really challenging. There's lots of places in Windows. It's a very complicated operating system with lots of dependencies. So there's lots of room for attackers to find different data structures, files to modify, et cetera. Also, because most attackers, once they get code execution on the machine, will be running as admin, you have to assume in your threat model attackers will be able to load arbitrary drivers that do arbitrary things. And so, again, we've turned to our T to provide a mechanism for attesting the security of the machine. And we started off by making what I would call boot time attestation. So when you booted the device, we'd be able to say things like, it started with code integrity, the hypervisor got started, there's no kernel debugger. That stuff is cool and useful for attestation, but I certainly wouldn't feel comfortable letting you have access to the Joint Strike Fighter plans just because you don't have a kernel debugger attached, right? There has to be a lot more. And so we started to think about how we could make runtime claims about the security of the system. And if you recall, one of the key attacks that we're most concerned about is an attacker loading a kernel driver and then using that to turn off all logging or detection mechanisms. So again, if you look into the Windows ecosystem, there's lots of people who spent a lot of money collecting logs, buying all kinds of artificial intelligence detection systems. And I can tell you the first thing my red team does and most attackers would do is get onto the box and just turn it off. And how would you know if there just wasn't anything bad happening on the system or whether the attacker has full control? You don't, right? And so our concept here was, again, to use our T to perform overwatch on the key data structure elements and runtime properties that will allow us to at least make I'll call it semi-hardware back claims about agents. So a good example of this is when Windows Defender is running on your device, it's running with a bit in its process flag that says this cannot be debugged. And the traditional way to nullify that is to load a kernel driver, remove that bit, and then all runtime access checks pass. But from our T, we can actually watch over these bits. We can initialize them and hash them basically at initialization time. And if the mutable property is ever changed, we can now fail to attest the system. And because we're doing this from the T, and we do appropriate token provisioning and attestation of setting up the T, and it goes all the way down through DRTM, we can actually make, again, semi-hardware rooted claims about software. And that means basically if you modify Defender, yes, you can do that, and you can pass that by loading a driver, but in the end, you will lose all access to the cloud because we will invalidate all your tokens as soon as you fail to provide a valid attestation. So in that way, we can somehow make Windows Windows tamper evident in the cases where we can't fully prevent a break. So in the end, Windows is rapidly advancing. It's obviously a challenging space to work in. It's used by, I think, upwards of 900 million people are running Windows 10 at this point, so there's a lot of work happening there. We have the gargantuan challenge of allowing people to run the games they want, legacy Java, some weird 16-bit Delphi app, and then also keep security going, and that is not an easy challenge. We also have new device forms, different architectures, different postures that we constantly have to support, and so this is something we're continuing to work on. And the researchers and community really help us with this. So again, thank you very much. Just 3 minutes over. Appreciate it. Thank you.
have you thought of giving it any backwards compatibility with standard passwords? Because the concern that I could see eventually happening is with the legal frameworks in the US where those aren't enforceable as something
Yeah, today we support passwords and biometric authentication in parallel, which from a security perspective, I don't think is perfect, but that's something, it's absolutely right. It's something we're gonna have to work through and eventually get to like FIP certification, common criteria, et cetera. And I think we're a ways from having that fully mature.
Or the lobbyist power you have getting to actually change the law so that those types of are enforced.
I wish I had some lobbyist power. I'm just like some engineer slumping around here trying to make stuff work.
Hey, I was wondering, I'm not sure if I misunderstood this, but did you say something about SMM attestation?
Yeah, I'd like to be able to attest SMM as secure.
How does that work exactly?
Well, for example, one way that could work is you could say, "Hey, SMM, I'd like you to use page tables only, SMM firmware writer," and then the hardware could set up page tables, lock them, and say, for example, give you a register or some other construct in hardware where you could read and ensure that those are locked. So you wouldn't be attesting everything in SMM. You'd be attesting that the page tables were locked, for example.
Okay. Is that actually happening, though, in hardware?
It certainly could.
Hey, I was wondering if, as part of what you're doing with the health attestation and the attestation flow that you described,
Yep.
is that extensible such that I could add more parts of the platform that I want to learn about and potentially collect that telemetry as part of the attestation flow?
So you want to like specify those arbitrary things?
Yeah, some kind of a list of something. It might not be arbitrary, but some list.
Yeah, so today we do have some policy controls in the MDMs who can pick this up, and we have a set of things. To be honest with you, there's very few customers, I think, who are like, what I really want to know is whether that SMM bit is set to this. And in fact, it's kind of complicated today. So I definitely see a world where we're creating more advanced policy authoring experiences, but at the top level, just telling people secure, yes, no, kind of thing.
No,
so yeah, that's a place we'd like to go.
Totally with that. I was actually thinking more from the researcher perspective.
So here's the good news. It's not good news for a researcher, but if you are a security company, we do have an API that you can use to call into our attestation service, which has a pretty flexible set of primitives that can come back that you can use to create higher level policies. I'd eventually like to get that to the point where it could be used by anyone.
Cool, thanks.
Yeah. If you've used like safety net on Android, that's kind of what I was thinking. Yeah.
So you had one piece where you were describing, I think, Windows being locked and somebody coming up and accessing a DMA port that might trigger the SMI handler, but having Windows have no response to that. But the platform still would, right? Potentially.
No, sorry, it wasn't physical access to an SMI handler. It was, hey, I want to plug in a Thunderbolt device. And you should never need to like have a new Thunderbolt device while you can't log in. So our concept is like, most of the risk is I'm introducing a net new Thunderbolt device that this system's never seen, but the machine is locked. And our calculus was, we're not going to break anybody's like use case by just blocking that from happening until the user logs in.
Sure, but that would only be, but that's only at the Windows level, right? Like the platform still responds. You still trap into the SMI handler when that happens.
That's right. So fault injection and other things are totally viable in that situation. And that's why we try to define this, our threat model as like casual, because we think that's a whole other level of stuff that we'd have to do on this broad OEM ecosystem.
Sure, thank you.
It's definitely something we do on Xbox, but or at least it's in our threat model on Xbox.
I had another question, sorry.
Yeah.
About, in one slide you mentioned UFI as a dumpster fire, this is why we're doing DRTM. On the other
No,
hand,
there was just a picture of a dumpster fire. I didn't say it was.
Fine. On the
UFI's
other
amazing.
hand, you're saying we're going to start turning on IOMMU early in UEFI.
Yeah. In our firmware that we upstream to the open source on GitHub now.
Okay, so you trust
So
that
if you're
on those
a dumpster fire, you can like extinguish the fire by grabbing our code.
All right.
Or core boot if that's what you like. That's fine too.
You had at some point in your slide deck, I think you had the measurements were done, your VTL is 0.
Measurements on what, sorry?
Done in the VTL0 for the octagon.
Yeah.
But
Those were examples, yeah, just boxes.
sure, but wouldn't that mean that if you compromise VTL0, that blows
So-
apart everything else because that's where the measurements are done?
We're in this space where we have in VTL0 an agent that measures some of the things we can't just get directly mapped from our secure enclave. And we try to protect that by, again, using an overwatch on that particular image. So we use HyperGuard. It is not the ideal design. It's where we're at today. And we'd like to get to the point where all attestations and measurements are done purely from the secure enclave. But that's actually taking a lot of things, including hardware changes, to get to.
Could you expand on hardware changes?
No.
Hey, just so that I'm clear on what you're proposing. So you're declaring...
Built a lot of this stuff, so
yeah, so you're kind of declaring complexity bankruptcy on the STM and saying instead...
I didn't say that. I said the feedback I heard from the ecosystem is STM is hard. And the evidence is I never saw an STM in production. That's all I was saying.
Okay. So instead you're proposing to have some kind of range registers and hardware and lock these and attest the state of those. Like this is an additional hardware. I'm not aware of such a hardware feature existing. Does it already? I'm just not aware of this, or this is an additional thing that you're hoping to push to vendors, or how?
You should read closely in all upcoming specs. Your answers are there.
Right.
I don't run a silicon company. I'm not in a position to comment on what exists, when, or where. I'm saying that I would really like to have SMM attestation in future hardware platforms because it would allow you to make stronger claims around TXT.
Okay, but it doesn't allow you to
And you've let silicon vendors know this.
And I may have let them know this, yes.
There's a feature called Intel runtime BIOS resilience,
Which is linked here.
which is like in there. You can go look at that and see what's available.
Brian.
I'm not trying to be obtuse. It's just I can't comment on stuff. I can comment on OS all day. I just don't own hardware, so.
Speaking of OS, Hyper-V.
Yeah.
Does that mean you're interested in STM? First of all, great to see. Thank you very much for being here. And
Yeah, of
talking to
course.
us. And great to see Microsoft getting back on the DRTM wagon.
Yeah.
Does this mean that Hyper-V is going to have hooks for loading STMs and stuff?
That's a great question. I don't know. I don't know if you're asking if we're going to take our Hyper-V firmware, like the stuff we load, and make that kind of STM compatible. I'm not aware of anything like that. I think our general strategy, and I'm not the Hyper-V expert, is to keep that as slim as possible, have a small attack surface. But that's an interesting idea.
Thank you.
Awesome.
I had a question about
Question.
about virtualization in two ways. So we,
Yeah.
in the open source side, we run Windows, of course.
Yep.
Is there a way to make Windows boot faster, maybe by not having to emulate all the physical ancient hardware? That we would optimize Windows for a virtual hardware.
Yeah, so I guess you're saying like, hey, could you like abstract away some of the stuff that might be slow by creating some kind of like new HAL layer? It's definitely an interesting idea, and I think we're looking at various optimizations around that. I don't think we're going as far as to have like a bare metal hypervisor that would abstract that away, kind of like KVM QEMU would. But I think it's an interesting idea, and like one of the things I thought was really cool is LF Edge I've been looking at, and I know there's some talk here. I think that's a really interesting concept for doing that.
So you talked about runtime monitoring in several examples, and both with software constructs and with possibility of future hardware features.
Yeah.
Like, it's sort of scary to me to have such an obvious, juicy attack target, right? Where if you get control of that thing, then all your data exfiltration wishes are granted. Can you just comment?
Is that like, are you thinking the secure kernel is the juicy target there? That's our T, essentially.
Well, the actual example I have in mind is I've seen unnamed proposals of abusing something like PCIe address translation services to have a really privileged peripheral snoop host memory.
Right.
Ostensibly to monitor like kernel code page integrity, but that thing is so powerful that I sort of don't like design. I have a hard time with that design. I just wonder if you had thoughts along something similar.
I mean, I think this kind of goes back to the old blue pill paper, which is like, yeah, if you can get an invisible hypervisor that has control and everything, you you're in the matrix, man. And I think our general approach there is to, when you're booting Windows, to try to have CPU-based trust, bootstrap trust for our hypervisor that would take over control of the spooky functions. In reality, the pace that hardware virtualization capabilities are moving at, it's going to be hard for us to keep there, but I would say our strategy is to boot our hypervisor first and use that to gate access to some of the more scary functions.
Okay, but from a conceptual level, you think that having a highly privileged thing that can monitor, somewhat invasively monitor many parts of the system still has security pros that outweigh the cons?
I mean, I think that's a glass half empty approach. Like, I would also be like, think about all this cool virtualization performance we could get out of this, right? I think that's kind of the nature of the system, which is we have limits for our security boundary. If you have a renegade hypervisor that can get loaded on the system, for sure bad stuff can happen. I'm not sure it's in the limits of our current capabilities to guarantee that can't happen unless our hypervisor's been booted, et cetera, et cetera. So it's just, I'm not saying that that is implausible or even not a bad thing. I just don't know if I can make strong security claims around that today.
Thanks.
All right, well, thank you very much
Cool,
to Dave.
thanks.